Sorry?
Can we get through it by the end of May?
No, I mean, I think maybe today I can just go through the absolute simplest example of residues of this Grassmannian integral, and talk about in this very simplest case we understand almost everything about it, including the connection with polytopes, and including well, and I'll tell you why we need a connection to something like a polytope picture associated with residues of this integral. Yes.
What do you mean by residue? Because do we have function? Do we have?
Think of it as a form. So think of it as a form, and it's a simple residue. So
So you have a simple pole, so you have a
yes.
of the dimension 1, and again it's a form on it.
Exactly. And we just keep right. Well, sorry. And then we keep going till we get to a point.
Oh.
So
Take a torus around.
right. It's as if we're doing a contour integral on a torus, surrounding quote unquote the pole. I mean, if I had a function of two variables, or if I had something like this, and if it was a g of x and y over p1, two polynomials, p2, then I would define what I'm defining as the. This is what I learned in some chapter in Griffith and Harris. So maybe I assume it's standard, but I look for the places where I put both of these to 0. So I look for places where p1 equals p2 equals 0. So that happens at some x star, y star at some point. And then the residue is just g at x star, y star over the determinant of the Jacobian dpi by dxj. Right, okay, at x star, y star. So that's, so I locally go to the neighborhood where these guys vanish. I change variables. So it's du over u, dv over v, and then I define that residue to be 1.
It depends on the order.
Yes, and it does depend on the order. Absolutely. It depends on the order. So it's the
On the order
right.
of what?
It's the order. It depends on the order of presentation of the polynomials that I'm setting to 0. So it's naturally alternating in the guys that I'm setting to 0, because I don't put absolute values around that determinant. So making it so the natural holomorphic object is naturally alternating.
Okay, but yeah, can I ask? Does that answer your question, Pierre? Because I have another one.
No, I don't think it finishes the answer.
Okay.
What if there's only one P1?
Then there isn't a residue. Then there isn't a standard residue.
So you care only about the 0-dimensional.
Yes. However, now having said that, these are what we call simple residues. So the ones where you can set, there's as many polynomials to set to 0 as you have degree of the form. Right. That's right. This is a situation where it's right.
Simple pole. In fact, it's a more complicated formula, but there is still enough residue.
Right, exactly. In fact, that's so, and this formula ends up needing that more general residue. So indeed, as you say, all that matters geometrically is that there is a preferred point out there. Whether or not you interpret that point as being the intersection of several zeros of these polynomials, or you get there some other way, there is always some notion of a residue. Now, just if in our own personal language, we make a there's actually no fundamental distinction between them, but this sort we call simple, and the other sort we call composite. And just to give an example, so if you have a function of 3 variables, and you have something that looks like that, so there's officially only 2 polynomial factors downstairs. Officially, there are no simple residues, but there really is one. I mean, I can put x to 0. And on the locus of x equals 0, this guy factorizes into yz. So it does make sense to talk about, there is a privileged point here, x equals y equals z equals 0. And so it does make sense to define the residue at that point to be 1 still. Now, that's actually different if I put a plus epsilon there. Then it's really different. Then the geometry is really different, and we don't know what to do with this situation. But interestingly, we never run into this situation. Okay? We always run into a situation when we talk about residues of this Grassmannian integral that roughly speaking, you have all these minors. So you start off life just putting minors to 0, right? And you rapidly see that you just run out of them. So there isn't enough, I mean, we can do the counting, but if you go to high enough k and n, there isn't remotely enough minors downstairs in order to fix all the integration variables. But what happens on the support of one minor, the next one over factorizes. Exactly, just like this example. This is the baby example. Factorizes into many, many of them, such that there's always plenty of factors left in order to be able to define a residue. I bring this up only, I bring this point up, A, because it's ultimately, for the very simple example I'm talking about, in the most simple example, it doesn't come up, they're all simple. The generic residues of this integral are all of this form. They're all composite like this. And part of the reason, this is one of many questions I think probably already has a very natural mathematical answer, and we just don't know it, is the question of how you talk about residue theorems when these kinds, when you mix up these kinds of poles with these kinds. I mean, there's the global residue theorem that tells you about the sums of simple residues vanishing, providing that things vanish at infinity appropriately. But we don't know at the moment the generalization of that theorem to take into account these sorts of residues. Maybe it's very well known and we don't know it, but we don't know it.
Well, I have a question. I mean, you can certainly imagine examples where there's, say, a point in 2 dimension. There are two where you have one of these things, and there are two essentially different non-homology equivalent tori in the complement, and you get different residues for the two of them. That is, the residue, to give the residue information is not enough to specify the point. You need some extra data. Do you ever meet such a thing? No, and I didn't know I didn't realize that was possible. If you just have, I mean, of course, we can have many solutions of these two, but you're talking about something that, even at a given, I see. More than simply the orientation, roughly speaking, which is just given by specifying the order in which the polynomials are presented. Right. No, we've never run into that, and I didn't realize that it was possible. It's not non-singular. Look at that one. No, in that. Oh, yes. In this kind of situation, right. So all I can say, right. So right. So you're saying in this sort of situation, it never arises. In this sort of situation, it could well arise. You're right. I mean, for example, even here, even here, it's sort of important to first put x to 0, and then see that you have that the other guy's factorized, versus trying to do it the other way around. Absolutely. So all I can tell you is that we empirically know that all the guys that we need, that we ever run into, that definitely participate in residue theorems, in the sense that we know there are identities that are satisfied between all these objects, just empirically. We need these identities physically, et cetera, but we've always found an order in which it's possible to put things to 0 sequentially in order to do what we did. That's right. Right. Particular torus, and that's the one you're talking about. Yes, that's right.
So
but
no ambiguity. I mean, you got your minors down in the denominator.
Yes.
And if you do it different ways, set things different to 0 in different ways, you're not going to get.
We have not run into situations. We have not run into situations where, with the same set of minors, we found essentially different, other than signs, essentially different ways of putting them to 0 to define a residue. But actually, you know, what we've started understanding. We started understanding how to even label the residues of this object, be they simple or composite or whatever. And so we think that there is a. It's not a statement about. It's not convenient to talk about the points by specifying the minors that are vanishing. It's a very cumbersome way of doing it. You really specify the geometry. So you know you have this point in the Grassmannian. You have, I mean, if you think of it very concretely as all these
n k-dimensional vectors, and then it's just giving a list of who is collinear with who is inside. You know, you have a big plane, you have a big k-plane, and then you have inside that k-plane you have lower dimensional planes, and some of the points belong to the lower dimensional ones, and inside them you keep going. There's a sort of Russian doll structure to just even classifying the residues. And with that Russian doll structure, we even have some understanding for what some of the residue theorems are, which definitely mix up simple and composite in some interesting way.
So you're saying you
yeah.
have a geometrical way, sort of a hierarchical.
Yes, we have a hierarchical way of sort of going down to the interesting residues in the which is critically dependent on, very critically dependent on the cyclic minors downstairs. Again,
Yeah.
you know, that structure is absolutely critical. So yeah.
Right, and then you can classify. Right. Right. Right, that's a good way of thinking about it. So, yeah. So can I get back to the question that maybe this is too long to make a to give me a full answer, but I'd just like a hint. How do you go from these residues to the actual integral?
Oh, how we go from the okay. So what we do is that.
It seems like a lot. It seems like
No,
a
it's
big
not
step.
long. No, in fact, we have a completely explicit formula. We have a completely explicit formula for the entire answer. A completely explicit recursive formula for the entire answer.
All the residues you're saying.
Yeah, I think if
Is
you
that
know.
a standard thing, or is it not? Is it
No,
very
it's not.
peculiar to this model?
Oh, I mean, so first of all, it's very peculiar to this. I mean, it's quite amazing that some contour order involving Grassmannian has anything at all to do with the amplitudes that we care about. That's the zeroth order point, right? Right.
That was still at the level of.
That was still at the level of these of the residues on both sides. That's right, right. But
the real problem on the right side.
right.
Is
Is the whole, and so what I'm saying is that there's an explicit recursive formula that builds up not just the residues of the quantum field theory answer, but the full integrand of the quantum field theory answer. In terms of the residues of the Grassmannian, that's right. And just to maybe give you a just to give you a rough idea, remember the quantum field theory amplitude is a function of these points that are points in CP3, and then also lines in CP3, right? So we had these. What I called AB. So a one loop amplitude would, for example, be a function of points in CP3 and some line in CP3. And the way you get this is it actually starts off life as one of the residues of this Grassmannian integral that depends on the points separately, ZA and ZB separately. Okay. And then what you do is and literally. A and B, so if I had particles 1 through n, then A and B live between, are sandwiched between, there is a cyclic structure everywhere here, so A and B are really sandwiched between n and 1. So this is a function of everything including ZA and ZB, and now it turns out that as a function of A and B, if you freeze everything else and just look at it as a function of A and B, that, and if you furthermore just freeze the line AB, and move A and B along the line AB, that this object has a natural simple pole. And so you just compute the residue on that simple pole. And what you're left with is just a function of the line AB. So roughly speaking, you're doing the integral.
You're telling me that these can all really be reduced.
Yes, they can really be used. So if we understood everything about these residues, right.
Or is there, what's the special structure that allows you to do that?
Well, I mean, so that there is, I mean, the sort of the, roughly speaking, the reason we can do any of these things is because even though we don't know the whole quantum field theory answer using Feynman diagrams, the Feynman diagrams, there's a property of them, which is that we know what their singularity structures are. So roughly speaking, we're determining the amplitude from knowing its singularities using a whole sequence of Cauchy theorems. And it's really possible to do it with little one-dimensional deformations, one step at a time, right? But there's nothing really fancier than that. Again, the sort of the remarkable thing is to recognize the sorts of terms that show up in this recursive determination of the answer in terms of Grassmannian residues. But yes, but so you know, and so you can see how all the statements that I told you last time are sort of contained in here. You start off with something that depends on 2 extra particles. If you do a partial residue on this guy, if you compute a partial residue moving A and B along the line, right, partial residue gets you to a function of the line. If you kept going and moved the line around as well and computed the residues on that, you would get what we would call, in field theory, a leading singularity of a residue of the integrand, which would be a residue of the Grassmannian, right? And it's all this is related to a bunch of simple rules that we found for putting together, you know, if you have a GK1N1, GK2N2, you have residues of these guys. You want to build residues of some other Grassmannian. There are some simple rules that allow you to fuse residues together to make residues of a higher one, increase the number of particles, decrease the number of particles. There's 4 basic building blocks for how you can take within the Grassmannian itself, take residues and build newer ones. And so just using those basic tinker toy operations, all the things that occur in this recursive formula.
So really
Right.
everything, all the guts
So,
is the
so really all the guts is in the, I mean, I could talk about it in infinitely more detail, but all the guts is really in understanding the structure of this contour integral.
And still 2 more bookkeeping questions. When you were describing things, it was about, we were apparently getting functions, and now you want forms.
Yeah.
And also with the odd variable, something even more complicated.
The odd, so if you want, think of them all as forms. So the amplitudes themselves are just rational functions. The amplitudes themselves are just rational functions. And so the rational functions map to residues, which are also functions of the Grassmannian, of that contour integral. That contour integral, okay, there's some, it is an integral, there's some form upstairs, and I compute the residue defined by points as we just discussed. So the loop integrand is a form, is really a form. There's some, you know, I have to integrate over all these lines. And I'm telling you that you can get that form. Yeah, I mean, I think a fair way of saying is I can get that form, roughly speaking, by starting from starting from this bigger Grassmannian, which is a big form, and before chopping up all the d's upstairs to take it down to a function, I stop with 4 of them left at the end, and so it really is a form, which is a function of the line, which is a function of the line which is left. Did that answer your question?
I think, I guess you will do it later, but I got confused this time about what was exactly the space of this big matrix I did not understand.
Okay, sure. Yeah.
You're going to give us a simple case?
Yeah. So now, yeah. So maybe the well, the only disadvantage of the simplest possible case is it's a G1N, so it's really it's not much of a Grassmannian, but it still has enough. The general formula that I wrote down was so maybe we could just talk about this formula in general for a second. Maybe that was so. And let me just say very explicitly what we mean by all the terms here. Okay. So I'm integrating over GKN. So here I've imagined that I'm taking my, I'm parameterizing the point in GKN by, let's say choosing this, let me just choose these coordinates by parameterizing the k by n matrix in this way. We can do it any way we like, but so then I have my k, my n minus k by k variables. Right? Yes. It's, and I view. Sorry?
Then you view it as the image of a map from CK to CN.
Yes. Yes. Exactly. Right. So anything I do with this, so anything I do with this needs to be
Invariant by GLK.
exactly. Anything needs to be invariant under GLK precisely. And so first of all, so let's just look at that. So separately, this guy is invariant under GLK, right? So this is so I have a delta of a, I mean, I have a delta C1A. Oh, sorry, these were Z's. ZA, delta of C2A, ZA, right? Yeah. So if I think about this. Right, if I think about specifying my k-plane by giving a sequence of n-dimensional, k n-dimensional vectors, right? So the first one is C1, so A runs from 1 to n always, and my index alpha runs from 1 to k. So I'm just forcing, so these delta functions are just really enforcing the picture I drew for you before, that there was some preferred 4-plane out there. There's some plane ZA. There are 4 bosonically. There's 4 components of this ZA. So in this n-dimensional place, in this n-dimensional space, all the external data, all the data about what is some itself, some 4-plane. Okay. So there are some. Oh, well, right. So I can think of them right. So I can think of them as n points in CP3. But in this n-dimensional space, I can think of those n points in CP3 as specifying some 4-plane in GKN. Okay? So, sorry, some 4-plane in this n-dimensional space. So it's some element of G4n as well. If I simply take.
This is where the observable comes in, right?
Right. This is all the data about the particles, all that stuff, is just specifying this 4 by n matrix. I just Z1, which has 4 components, Z2 has 4 components, up to Zn, right? This is some 4-plane in n dimensions. These delta functions are just telling me, so let's call this 4-plane in n dimensions Z, okay? These delta functions are just forcing this k-plane that I'm integrating to be orthogonal to this, to be orthogonal to that special 4-plane. Orthogonal. Delta of C1A, Z, C2A, Z, summed over A. Yeah, I'm forcing those to be 0. So there's this privileged 4-plane, and then I'm integrating over all k-planes, but not all k-planes. Over all k-planes restricted to be orthogonal to this particular 4-dimensional plane. So really, I'm really, yeah.
You're really in a smaller Grassmannian.
Really, I'm in a smaller Grassmannian, right?
Smaller Grassmannian, the thing doesn't have such a beautiful.
Exactly, and that's somehow the sort of entire. That's somehow the entire point. Is that really this is an integral over GK minus 4n, right? I mean it's, but I can't specify. But the measure on GK minus 4n is something very, very complicated. So I'm inducing on GK minus 4n some measure from this simple cyclic one on GKN. That's really the way of saying it.
In the absence of this delta function, or if I were to integrate over it, I would get 1.
If you integrate over.
So in other words, is this a normalized?
Yes, absolutely. And again, yes.
It's a little artificial to put this scalar product on Cn.
Yes.
So to be more canonical, something is in a space and something needs to be.
Right. Yeah. So Yeah, I think you're absolutely right. You're absolutely right. It's not really that. I mean, said in my language, nothing forces me to put the indices downstairs. So it could absolutely be its dual. I'm sorry. Yeah, it's really its dual. I should have said it that way to begin with. Sorry about that. Yeah. Yeah. Okay. But actually, let me just. There's actually a very important point here, which is that. And this is where the supersymmetry comes in. This is what these fermionic variables, its real purpose in life is that if I simply took this bosonic k-plane in n dimensions and I wrote down those delta functions to enforce just what we said, it would not be GLK invariant. It wouldn't be invariant under the G part of GLK. It's not invariant under rescaling everything, right? And so the entire purpose of supersymmetry here is to. So that's why I have this factor which is delta of c dot z. And the entire purpose of supersymmetry is to pair these z's with some Grassmann parameters eta, such that under G now the fermion Jacobian cancels the boson Jacobian. They go the other way because they're flipped. And so this is honestly GLK invariant. Okay? So that's somehow that's a really interesting. It's a really interesting link between really being able to talk about Grassmannians, being able to talk about something that's GLK invariant and supersymmetry.
But you have
right.
no Grassmannians in the integrander, do you?
No, I do.
Not
Yeah.
these
Oh no, Grassmann variables. No, that's right. No, sorry. Right. That's right. It's a bosonic Grassmannian. It's a normal Grassmannian. It's a normal Grassmannian.
It's not a supersymmetric Grassmannian.
It's not a supersymmetric Grassmannian. It's a normal Grassmannian, but it's supersymmetrically orthogonal to some four-plane, and the supersymmetry is there to allow this to make sense as a statement about Grassmannians, for it to be GLK invariant.
So have you already somehow, when you've done this, you've already traced out the Grassmann variables when you
On this side?
Yes.
You know, we don't know. We're very used to having everything have Grassmann partners, but it just doesn't in the story. It's a purely bosonic object. That's right. And in fact, as you'll see in a second, or whenever we get to it, when these guys have even though the sort of purpose in life of these Grassmann parameters of supersymmetry here is very different than the normal ones that certainly we're used to in physics. They cancel something, it's very geometrical. It's just to allow you to talk about things, to allow you to talk about Grassmannians, bosonic Grassmannians. And we'll see that these polytope pictures that I'm talking about are incredibly bosonic. They're really polytopes in some honest bosonic CP4 or some honest bosonic Grassmannian. And then, of course, in the end, we have these Grassmann variables as our data, right? But you're just putting these things, these Grassmann variables go in. It's just some particular way of parametrizing something that's completely bosonic. The whole story is much less supersymmetric in the Grassmannian or in in this language than we're used to.
Well, I thought maybe you somehow traced them out.
No. We've never had them to begin with. We've never had them to begin with. Yeah, we've never had them to begin with. And then just to maybe finish the story. So then in order for the integral over the Grassmannian itself to be GLK invariant, the sky upstairs isn't GLK invariant because of the G, and I just have to have n sort of a net n minors downstairs. And so you need n minors, and so there they are. And this is, as I mentioned before, it's aesthetically the nicest one. It has a cyclic structure in it, which we know the answer has. There are many other things you could have had which are cyclically invariant. I mean, take anything and multiply it by all of its cyclic images. But this is somehow it's the simplest one. And finally, apart from aesthetics, I mentioned, I think at the end last time, the claim that if you want to write down superconformal invariants, so GL4/4 invariants, any GL4/4 invariant, this is the claim. I don't understand the proof in detail, but the claim is that any GL4/4 invariant is an integral of some measure, but over the Grassmannian of this object. Any one is of that form. Any GL4/4, yeah.
So from that, you don't see this particular
No, that's right. So just GL4/4 alone, though, just GL4/4 alone is in one-to-one correspondence with some integral delta 4 for C dot Z, which is already a non-trivial statement. I mean, because it's trivial to build bosonic. It's trivial to build bosonic GL4 invariants. You know, you just make things out of cross ratios. The point is, it's very hard to supersymmetrize random cross ratios. In fact, the only things that are fully GL4/4 invariant are integrals of this form. So that's already some function of C there. That's already one interesting statement. And the second one is that this full Yangian symmetry, not just the GL4/4, but the full Yangian of GL4/4 is in one-to-one correspondence with that particular measure, with the cyclic minors.
That forces it.
Right, and that really forces it. So somehow we're doing,
Understand
yeah.
that that's an important thing to do. We don't have to be physicists, we just have to believe it in the Yangian symmetry.
Yes, exactly. So somehow, if nothing else, this is the answer to the mathematical problem. Write down all Yangian invariants of GL M/M. Is the residues of this integral. And actually, the question that you've raised a number of times is, what are we talking about? Functions, talking about forms, whatever. I think that what we've done in building the loop integrand is a sort of hack job of finding things that are not just functions, but forms that are invariant under the Yangian. And it would be wonderful to say that more formally and more properly than we've said. We have not phrased it in that language, but I'm sure that that's what we've done. So the thing which is on quite solid footing is that all functions that are Yangian invariant are these guys, but forms that are Yangian invariant is probably the integrand, and everything else that we're talking about.
So can I ask? This is really for Bob or Pierre. So are such integrals? Are you familiar with such integrals? No. Okay.
Well, I mean, especially since I ran into your papers with Gelfand in the early '80s, I thought, oh, we're in Fat City, you know. But I guess the novelty is the particular cyclic structure, and I guess the cyclic structure is not totally obvious from the point. I mean, I guess this is really where physics makes a big entrance, because we want something with this cyclic structure because of the scattering amplitudes.
Yeah, but my question
But-
is,
Ribbon
right.
graph stuff, right?
Right, exactly. It's just that, right.
so, but do you integrate something with determinants? I mean, is that typical of what you do when you do these integrals over when you compute volumes, or I don't know what you're doing because I don't know the literature at all. Don't know the stuff at all. Do you integrate minors at all? Is my question.
Yeah, I think that's a natural.
But it's just that you don't integrate them in that particular form, or I'm just trying to understand what kind of thing you do.
Yeah, sorry, I can't really answer that completely now, but I
Okay.
believe that integrating minors is a very natural thing that has been done quite a bit.
I mean, the volume
I
from
think we did that.
Grassmannian is written in terms of minors.
I would think so, yes. Okay, thanks.
I mean, any one of these things define the Schubert cycles, blah blah blah. So you know that this is this part of the story is, I mean, having minors is completely, totally canonical. I think it's this particular cyclic structure. It's a particular structure. Yeah, it's a particular cyclic ordering. Yes, exactly. That's right. There's another thing which is sort of, yeah. Anyway. That's,
So I guess the planar graph structure has to do with Yangians.
absolutely. Yeah, I should say this is only true in the planar limit. This is only true for planar diagrams. The fact that the answer has a symmetry is only true for a planar diagram. Okay, so let's maybe yeah. Yeah, so before giving the example, I'll just repeat one more time that the one general thing I said last time, which is that these objects not only give us the Yangian invariants, but they somehow tell us all the relations that they satisfy from residue theorems. So each Yangian invariant is a residue all by itself, but there's also tons and tons of relations that they satisfy, which are a consequence of residue theorems applied to this big contour integral. And they're both important, both having because when you, the relations between these invariants encode things like locality and unitarity. So there's the very, very important physics is associated with the fact that these objects satisfy very non-trivial identities. And in fact, before we knew about the structure, we were just staring at the answers, we're staring at the invariants, and then seeing these incredibly non-trivial identities that they had to satisfy, and not being able to prove them directly at all. I mean, they were just impossible to prove. But it's somehow interesting that they're not only is it spitting out the invariants, but it also knows something about all the relations they satisfy. It's not just, I'm just stressing, it's not just the answer. It's not just each individual residue. It's that together with residue theorems, which is, I think, all the interesting content of this object. Yeah. So again, we could take this and actually perhaps we can just do some basic counting right now. So we as we said, we really have on the support of those delta functions. So we start with k times, and we start with k times n minus k variables. But really it's k minus 4 times n minus k plus 4, right? Really, that's the number of variables we have, because on the support of those delta functions, which tell us that this k-plane has got to be in the complement of that 4 plane. It's really a k minus 4 plane in
Did you take into account yet the VLK invariant?
Yes, yeah. So I mean, if we do the yeah. So if you like, we start off with k times n minus k squared for the GLK. Okay. I mean, if I want to do the counting very explicitly, and then I would say it's minus 4k, right? Because I have 4k delta functions. So okay, so this is what it is. So it's kn minus k. It's k minus 4 times sorry, it's k times n minus k minus 4k, right? So it's k times n minus k minus 4. So that's the number of that's the number of integration variables we have, and so you look, I mean, so you look for a that dimensional torus, and you do an integral over that dimensional torus to get the numbers out, and so the point is these things satisfy lots and lots of identities, and those identities are important. That's the last general comment I wanted to make. Okay, so the simplest case is k equals 1. Well, the simplest case is k equals 0. Then the answer is just 1. Okay, so we have nothing to do. That's actually already a remarkable fact because that's right. Yeah, sorry.
K equals 0.
Yeah, k equals 0. K equals 0. There's just nothing, right? It's a zero-dimensional integral. It's just 1. Okay, so this is just 1. And on the other hand, I told you that this computes leading singularities of the integrand, residues of the Feynman integrand, the loop integrand. Well, for k equals 0, I certainly have 1, 2, 100,000, any number of loop integrands. And so this makes a dramatic claim that the residues of all of those things are 1, and they are. Okay, so that's that's already a non-obvious statement, which this makes obvious. But it isn't. But it's not too interesting otherwise. So from the point of view of this object, so let's go to k equals 1. Okay, so for k equals 1, we're just doing an integral over g1n, so it's just cpn minus 1, unfortunately. But let's just do it anyway. So we would write dc1 over c1 up to dcn over cn. And this is the modulo of GL1. I'm not sure what the right way of, well, anyway. It's the standard measure on CPN minus 1. So times, so I could write delta of C1 Z1 plus Cn Zn. And then delta of C1 eta 1. So this is delta 4, another delta 4 of C1 eta 1 plus Cn eta n. So that's the object we're talking about. And actually, if we just count to r, so if k equals 1, we have n minus 5 variables, integration variables. So the simplest case of all is going to be n equals 5. So let's first look at n equals 5. Okay? So if n equals 5, then I have here dc1 up to c1, dc5 over c5, delta 4 of c1 z1 plus c5 z5. Sorry to write it down again. Delta 4 c1 eta 1 plus c5 eta 5. Now, this modulo GL1, I can use to set any one of these c's to 1. Let's say I use it to set c5 to 1. Okay? So if I set c5 to 1, this is now literally the integral dc1 over c1 up to dc4 over c4. Delta 4 of z5 plus c1 z1 plus c4 z4. And then a delta 4 of c1 eta 5 plus c1 eta 1 plus c4 eta 4. Okay, so it's clear that we're freezing all of these integration variables with these 4 delta functions, okay? Because this is it's a 4 vector, so I can expand this 4 vector as a linear combination of any as a linear combination of the other 4 vectors, and I can solve for the coefficients. So if I take z5 is equal to negative c1 z1, negative c2 z2, negative c4 z4, then if I contract this, so whenever I write down a, b, c, d, I mean that I'm contracting the corresponding z's, just taking their determinant with the epsilon symbol. Okay, so if I take 5, 2, 3, 4, then this is just negative c1, 1, 2, 3, 4, and everyone else is 0. So I'm just expanding a vector in terms of 5 vectors. So I solve for c1 is equal to 5, 2, 3, 4 over 1, 2, 3, 4 with a minus sign. Similarly, I solve for all the other guys. Okay, so c4 is negative 5, 1, 2, 3 over 1, 2, 3, 4. And then if I just then plug it in here, you can see. Let me write down the answer. So the answer is equal to something that we denote as 1, 2, 3, 4, 5, which is delta 4 of eta 1, 2, 3, 4, 5 plus eta 2, 3, 4, 5, 1 plus continuing cyclically eta 3, 4, 5, 1, 2 over 1, 2, 3, 4, 2, 3, 4, 5, 3, 4, 5, 1, 4, 5, 1, 2, 5, 1, 2, 3. Okay, so that's what we get. So this term, so I just solved for all the c's, so that gets rid of the delta function. Then I have to plug in the c's into the dependence on these Grassmann variables. So you see how I get that, for example, the coefficient of eta 1 should be C1, which is, oh, sorry, I totally screwed this formula up, sorry. So this is, oh, that was C4, sorry, right, that's right. So this is 5, 5, 2, 3, 4. Okay, so there it is, 2, 3, 4, 5, and it was over 5, 1, 2, 3. Sorry, over 1, 2, 3, 4. But if you just, anyway. And the 1, 2, 3, 4s inside here cancel exactly the ones that you get from the denominator of these formulas, and this is just what you get. Okay, so that's now this delta 4 is really, it's a polynomial of degree 4 in the etas. So the etas are Grassmann variables. So if I expand this out, it has a piece that looks like, for example, there's a piece that looks like eta 1 to the 4th, 2, 3, 4, 5 to the 4th. That's a piece there. Yeah. So let's talk about this. Let's talk about this notation. If we just have a single Grassmann variable eta, delta of eta is just eta. The idea of this definition is that it behaves like a delta function under Grassmann integration. So if you have integral d eta of some a plus b eta, which is a general function of eta, times delta of eta, then you would like this to equal f at 0. You'd like this to equal a, which if you make delta eta equal to eta, it does. Okay? So this is equal to integral d eta a eta plus b eta squared, which is 0, which is a, which is f at 0. So that's all this is. If we have two Grassmann variables, then delta squared of eta is delta of eta 1, delta of eta 2, which is eta 1, eta 2. So yeah, so that's the general definition.
So you're gonna integrate all the etas together, or?
So the etas, remember, the etas contain all the information about the external helicities of the particles. So if I want a particular helicity, then I have to integrate against. Then I pick off different components in the expansion of this. Just think of this as a generating function. It's a nice Grassmann generating function for all of the different amplitudes that are actually there. Okay. But yeah.
So just to make sure I understand, so this n equals 5 case, you have a 4-plane, you're integrating over stuff perpendicular to that, that's a line.
Right.
And in that line, you're going to have, what, five poles? Your expression is going to have 5 poles, and
Except actually, in this case, so yeah, perhaps I should have said it geometrically to begin with. Here, there are actually no poles at all, because I'm integrating over G15,
yes,
which is CP4.
yes.
Okay, and so I'm demanding that it's orthogonal to this 4 planes. It's unique what it is. The plane which it's just the unique plane which is the complement. Exactly. Yeah. Sorry, that's right.
So it's just a single number.
Exactly. There are no integrals at all. So that's why it's a simple. So here everything. I wasn't forced to choose any contour, right? The delta functions forced everything. If I said another way, the delta functions are some poles I'm forcing myself to use in defining the contour. But right.
You're going beyond it.
That's right. We're going to go beyond, and then if we go beyond, now we have choices to make, and they're honest residues, and we've got to actually we compute them. But the simplest case is one where there's just nothing. There's a unique right. It's just unique. Sorry. Yeah. And that's just what it is. That's what it is explicitly. Now, if we move on to n equals 6, then there is a one-dimensional integral that we have to do, and so if I do this dc1 over dc6 over c1 through c6 delta 4 c dot z. Let me just be a little schematic because we don't actually have to do the computation. I mean, the structure of the answer is going to be obvious in a second. But this is going to be some one-dimensional contour integral. It's going to have 6 poles. I mean, if I just solve on the support of these guys, all the 6 c's are a function of one free variable. And in that free variable, there's going to be six poles in general. Okay? So I have 6 poles. Yeah.
So this gives you have 6 points in a complex line. Do those have some nice geometric
I think they're. I mean, they as you move the external data around, they move around. Yeah.
They move completely freely.
Yeah, they move completely freely. Interesting things do happen when they run into each other, of course. But anyway, there's nothing particularly special about them. So we have 6 points on the line. They're just moving around freely. Now, the residue on each one, what is the residue on each one? Well, it's extremely simple, because the residue on the one where C1 vanishes is I just put C1 to 0, then it's exactly the same computation we did before. It's as if I just had particles 2, 3, 4, 5, 6 in the formula above. Okay? So I have 6 residues here. I have the 6 residues from when I put C1 to 0. That residue is equal to 2, 3, 4, 5, 6. C2 to 0 is 1, 3, 4, 5, 6, and so on. Okay? And so here there's just a trivial Cauchy theorem, which says that the sum of all these residues is 0. All 6 of these residues is 0, and that turns into a nice identity for these objects. So we actually learn, if I'm careful about all the signs, we learn 1, 2, 3, 4, 5 plus 2, 3, 4, 5, 6 plus cyclic 3, 4, 5, 6, 1 plus dot equals 0. Okay? That's really the sort of, so for k equals 1, these are the fundamental objects, or these 5 bracket guys. This is the fundamental identity that they satisfy. And there's nothing new past that. So as we go to 7 higher particles, I mean, officially it's a higher and higher dimensional contour integral, but because it's so trivial here, all the poles are given by, I have to put enough of them to 0 till I'm left with 5 guys. So I might as well label them, instead of labeling the guys I set to 0, let me label them by the guys that I did not set to 0. I label them by the 5 guys. So the general residues at k equals 1 are just A, B, C, D, E. And they satisfy a 6-term identity, which is just the analog of that. I mean, which is A, B, C, D, E plus B, C, D, E, F plus cyclic equals 0. Okay? So those are all the residues of this most trivial case of this contour integral. And we see that they come equipped with a nice relation between them. This 6-term identity is a nice relation between them. Yeah.
In this case, you could probably prove the 6-term identity just by algebra.
Yeah, it's just Cauchy's theorem one at a time. It's that trivial, because oh, sorry. Also, even if you didn't know this, yeah. This is not so bad. This one is not so bad. Yeah, this one is not so bad. I mean, the only identities that this all follows from are the Plücker relations on the minors. So it's really just that. It's a glorious because that's all there is. But just the quadratic relations that are satisfied by these four brackets. Just the
Grassmannian is a projective variety has equations, and that's
right. Yeah, the higher ones are really impossible to guess algebraically. Right. This, I think, if you just ran into the object, you wouldn't guess that it satisfied it. Although if someone told it to you, you could then, with some effort, verify it. Right. Right. Okay. Now, just we're nearing the end of the time, but let me just say one or two more things about this. One of them is that. I mentioned that these identities are important for physics, and I just want to show you a concrete example of that. So,
are they Ward identities, or are
they? No. They have nothing to do with Ward identities. Actually, Ward identities have to do with gauge invariance,
or the symmetries in your system.
Right, but normally, the non-trivial ones have to do with gauge invariance, and we don't even have gauge symmetry here at all. We're not even talking about gauge symmetries in this formulation. So it's not that. But let me just give you an example of a physical object. Let's talk about the tree amplitudes for k equals 1. Okay? So there's some recursive formula, I haven't told you what it is, but there's some recursive way of determining what all the tree amplitudes in the theory are.
So tree means 0 loops.
Zero loops, right? And this is what the formula ends up being in this special case. It's the sum over I and j, running over all the particles, okay, of 1 I plus 1, jj plus 1. So this is not manifestly cyclically invariant. There's a special point, 1. That's because in all these recursion relations, you pick a special, you pick a leg to be special, and then you do some. But anyway, it's not manifestly cyclically invariant. Okay? Now that's very important, because if you look at each one of these terms, if you just look at the poles that are going to occur in each one of these terms. Let's not write the numerator, but there's things that look like 1 I plus 1 j. Then there's something that looks like I plus 1 jj plus 1. And then there are all the other ones that involve 1, right? This is the only one which is a physical pole, by which I mean, has this legal space-time interpretation that we talked about last time. All the rest of these are spurious poles. They're not, they have to cancel out of the answer. They cannot be there in the actual answer. And yet we're expressing the answer in a way that's dominated by spurious poles, okay? And that was a sort of identity that we needed to prove. We had these objects, not written in quite as nice a form, actually, but in a more complicated form that made it even harder to see the identities. But we had to see, how do we see that these non-local poles cancel? So some rational function identities that were needed to see that they cancel. It's related to seeing how it's cyclic. Let's say you wanted to prove that this is equal to, if I replace 1 by 2, I get the same formula, right? Well, that's a non-trivial identity. But if you could prove that identity, it would also prove that all these non-local poles are absent, because they won't involve 1. They would involve 2 on the other side. Okay? So you see that some identities were needed in order to establish independence on the point 1, which in turn established that the answer was local, for example. Okay? Now, how do you prove these identities? This just follows from the 6-term identity. Repeated applications of the 6-term identity prove this simple fact. It isn't 100% obvious. But I'll talk about what does make it obvious, which is a geometric picture, which interprets this actually as the volume of something, and a particular triangulation of a volume of some polytope. Okay. Now I think we've hit the hour mark. I'm happy to leave it here. I can also, it will probably take me another 20 minutes, half hour or so, to explain the polytope picture. Okay.
So if you wanted to do k equals 2, does that already become?
K equals 2 is already, everything hits you in the face. At low n, up to n equals 7 and 8, all the so n equals 7, I should have mentioned something. There is a natural symmetry between k and n minus k. Not n minus k here. N minus k minus 2 here, actually. Sorry, n minus k plus 2. So n equals 7, k equals 2 is like n equals 7, k equals 1. I mean, it should be related. There's a parity symmetry which relates them. So the really new stuff starts at n equals 8, k equals 2. And there, I mean, we understand k, we understand as I said, in a sense, we understand all the residues of the Grassmannian from this some Russian doll picture. But we know how to label them, and we almost know how to compute them. I mean, without explicitly taking a residue, just write a more direct formula for them. But all these statements, are true at the 1 minus epsilon level, and as I make more and more of them, I multiply those 1 minus epsilons more and more of them. But k equals 2 is understood incredibly well. I mean, in the sense that we have a very good familiarity with all the residues individually. We're friends with them, and so on. Yes, already at n equals 8, the first non-trivial example, you have simple residues, composite residues, square roots. I mean, they're already they become algebraic and not rational. There's no reason they should be rational, right? They should be algebraic in general. And indeed, they're absolutely, you get the square roots already in the first non-trivial case they could arise. Right. Well, because we have quadratic equations now. That's right. So now I'm just in solving the roots, the minors are quadratic. Right.
Is your delta functions that give it or not? Is the constraints from the delta?
No, actually, the constraints in the delta are linear. It's just because I'm putting a bunch of minors to 0. And the minors in k equals 2 are quadratic in the variables. So actually, the simplest non-trivial case at k equals 2, n equals 8, you can map to the classic Schubert problem, the old Schubert problem of lines in 4 given lines in P3 and finding a line that intersects all 4. That's so the residue here maps, finding the residues maps explicitly to that problem in the simplest non-trivial case. And there, when the lines are in general position, there is a square root. I mean, if you want to define the line that crosses all 4, there's a quadratic equation you've got to solve, and that there is a square root there. But it gets more and more interesting. It gets more interesting after that. But then there's lots of there are lots of amazing identities for things involving square roots written in terms purely of rational functions, for example. Of course, you sum 2 square roots with different signs, and all those things have some important physics interpretation. But maybe Bob, just to say something quickly, about what I just said, the sort of geometric picture behind this. You see, there's something a little bit funny, because that 6-term identity looks exactly like the sort of identity you would expect if you forgot about the fact that A, B, C, D, E was some function that I told you what it was, and it was just abstractly labeling a 4-simplex in CP4. So so this is it's the identity that you can chop up. That I think I learned that it's called the scissors. It's a scissors congruence identity. So the fact that you can take, well, the analog in CP2, the fact that you can take this triangle and write it as the sum of those 3 triangles. The analog of that in CP4 is a statement about four simplices. So I label the vertices by 5 guys, right? So I have a 5 tetrahedron, whatever you'd call it, a 4-simplex in CP4. And if you put a point in the middle and triangulate with the point in the middle, you get a 5-term identity. You get a 6-term identity. Okay. Now, so it's quite striking that these objects, which are really functions of points in CP3/4, right? The function of CP3/4 actually satisfy exactly the same identities as if A, B, C, D, E were labeling points in CP4. So on the one hand, the data lives in CP3/4. On the other hand, these residues are exactly what I would get if I imagined that the 5 particles were living in CP4 and were just giving the vertices of some tetrahedron in CP4. So that turns out to be more than an analogy in this case, because we can give a formula for that object as actually the volume of a tetrahedron in CP4, of a simplex in CP4. That I can say, that I can even say that, yeah.
There are 6 terms. What are you saying? Those 6 terms correspond to some aspect of a tetrahedron in CP4?
Yeah, if we take a tetrahedron in CP4, take a fixed tetrahedron in CP4, then put a point in the middle of that tetrahedron, and then triangulate, and then, huh? Right, that's right. So then that's the plus, yeah, that's right, exactly. So that's plus the whole. That's right. That's right. Yeah, right. Or I mean, I could also say it's a boundary of boundary equals 0 statement if I start with a formal 6 simplex A, B, C, D, E, F, and I take its boundary. But if I think of it directly as a tetrahedron in CP4, it's just the statement that, yeah, right, exactly. So right, exactly. It's the additivity. That's really the sort of crucial point here, is that when we think of them abstractly as residues, they obviously have additive properties. But in this case, in this very simple case, we can that additivity has a purely geometric reflection as just being the additivity of volumes in CP4.
So
right.
Okay,
Right.
great.
Right. So and
So you're going to fill us in on a corresponding additivity of the Grassmannian in two planes and four planes.
Exactly. So that's but it's a generalization of that picture
Right.
in general that we do not have. In the simplest case, where it's the G1n on the one hand, we can map residues to polytopes in fact to little tetrahedra and interesting contours like this. Interesting sums of these residues are some very nice canonical polytope in CP4. What we don't know how to do is, in general, take the residues of the general Grassmannian and give them a similar geometric interpretation. But we feel it must exist. There must be some geometrization of the residue theorems that are satisfied on the Grassmannian side. That's a very sort of abstract. Yeah.
Next time I'll tell you more precisely what he's saying about CP4, which I think would be useful, because he just said it in words, but he'll draw pictures. I mean, in CP4, before going to the Grassmannian in two planes.
Yeah. So there is already even before going to G24, there is something interesting in. Right.
Okay.
But yeah, we can do that
Let's all
next time.
hold that thought.
Sure. Great. All right.